Good afternoon, muchachos and muchachas. We're going to talk about trial design, METs, and GxE interaction now. So this is actually the first session about how to improve your breeding pipeline, how to actually improve your breeding approach. So just a very brief recap of what we've done so far. Agnes started with the product profiles and the market analysis. Eduardo yesterday presented the breeding scheme designer. Basically, what we think are two of the very three important pillars to make sure you got a well-functioning breeding program. You need to, as Eduardo explained yesterday, you need a target. You need to define a target where you want to go before you actually normally would start a breeding program. So you have something that you want to achieve. Once you have done this, mapping out your breeding program makes a lot of sense. We have done that with most of you, and now there's this tool online that you can use. We're not going to talk about data management, but we're giving you ways to do database breeding. So this is something that is kind of inherent to this. This is another foundation that is very important. And through the next couple of days, we're going to talk about all these things which are kind of built up like this pyramid. Today about field trials. Dorcas is going to talk about program size and genetic variance management tomorrow. And at the very top, you see there's genome-assisted methods. We're coming to that at the end, but I want to point out already now. Genomic-assisted methods, genomic selection especially, is often understood as that magic tool that can massively optimize your breeding program. And it's a good tool, but there's a lot of other tools which also can optimize your breeding program that we're going to talk about, and that are, compared to genomic selection, low-hanging fruit. So in general, we would suggest that this kind of build-up is a path you should optimize your breeding program before you consider this here, because this is easier to achieve, this is very efficient, and this does not require as much restructuring of your breeding program than GS does. So let's start with the field trials, but before we do that, I want to show this, which is a graph that I borrowed from another person's presentation, but I said last time already, probably this person borrowed it too, so no. What? It's an infinitive loop. Well, I sometimes feel it's a negative feedback loop. But anyway, so we're going to talk about a lot of stuff, and we've invested the last 1.5, 2 years to coming up with the answers to the questions you asked us. So this is not trivial stuff. We have had to invest a lot of time into literature research, into discussions, into running simulations, into talking to other people. And some of the results were also very surprising to us. So don't feel discouraged if you don't get anything at the moment. Knowledge, my impression is, works a bit like this over time. So you're sitting here in the course now. I'm going to talk about METs. And when you leave the course, you're hopefully here and think, oh, everything makes sense. Then we go to dinner, you have 2 beers, and back in your room, you're back here and say, well, actually, I don't understand anything, and I'm like, I'm too dumb to do this. But that's not the case. Take your time. It will take time. It will take a lot of repetition. It takes us a lot of repetition, a lot of reconsidering, and at some point you will be up here and understand everything and be able to employ it in your breeding programs. Again, it just takes time, and often there's like this negative feeling that, well, I actually don't understand it, and don't give up here, but move on, and it will work. Now, again, it's a lot of stuff. You probably won't be able to remember everything except you're super, super smart. I wouldn't. So we have these manuals in our toolbox which actually do cover a lot of the stuff we're talking about. It's a very, very valuable resource. There is, for example, these two manuals on design analysis, which cover a lot of the stuff I'm going to talk about. So well, you know, the presentations are sometimes a bit sparse. If you want it to be written down, there are a couple of manuals that are really worth looking at. Now, let's get started. Again, the stuff we're going to talk about in the next couple of days are answers to questions that the different breeders, including you of the programs we're working with, asked us. With regard to field trial, the most common questions were, for example, should we test in more locations or should we test more replications per locations when we do MET trials? What is the optimal MET field design to estimate genetic values and do selection accurately? These are highly related questions. Another popular question was about the checks. What percentage of check plots or replications do we actually need in our field trials to do a proper field trial analysis? P-reps has become apparently a popular topic, and people asked, well, what actually is it and how can we implement it and when is it useful? So P-reps is going to be one of the topics, and eventually sparse testing. So I'm not sure with these 15 to 20 minutes missing if we're going to cover this today. But that's not a problem because this is, well, I can tell you now already sparse testing requires genomic selection. So it's going to be picked up in the session on Friday anyways. And we did that last time as well. We covered sparse testing in the genomic selection method, in the genomic selection session. So if we're not covering today, don't be concerned, we're coming to that point. What I'm going to do is I give you a very brief introduction into the basic theory, which is genetic values, the effects of the environment and GxE interaction, and then we're coming to the results. And I'm going to tell you the results already now, so you can be prepared. And then I'm going to give you the explanations why these are the results. First one is test in more locations, at least in most cases, more locations rather than more replications per location. Second one regarding the within location field designs, which means alpha lattice, RCBD, whatever you use. Basically, use whatever you want to use as long as it is still a kind of design, as long as it uses things like replication, randomization, and so on. And minimize the percentage of statistical checks you're using. I'm going to tell you what I mean by statistical checks later. Very important if the people who do the analysis for you, like Johan and Bert, use linear mixed models. These suggestions that I'm giving you do not work really well with ANOVA. So if you still have to do it on your own and you're stuck with ANOVA methodology, this wouldn't necessarily work, and we need to find support for you to go to linear mixed model. This is a game changer. Include a genomic relationship matrix in your linear mixed models if you can. Hopefully you can. Otherwise, let's try to get to that point in the next couple of years. And use sparse testing to test in more locations. This is also, again, ordered in like a hierarchical manner. So this would be like the last step for you to optimize it. This is nothing you probably would do just as a first step to optimize your field trials. So I'm going to start with an equation, and I've only got two equations in this highly statistical topic, so hopefully this doesn't get too hard, and I think these are two equations which are not too hard to understand. This is something that you're probably very familiar with. How is the phenotype that we observe in the field built up? So as breeders, what we want is we want to estimate this with our field trials. Our surrogate of genetic value, the estimate or the predictor we select on. Marley has talked about this morning, the different kinds of blubs and blues that exist out there. And if we want to estimate, I don't know, a breeding value or total genetic value or whatever is necessary for our breeding program. So again, this is where we want to get to. Unfortunately, in the field, the only thing we can observe is a phenotype. And the phenotype is, of course, affected by this genetic value, but there are a couple of other factors that affect our genotype, that affect our phenotype, which are, well, these are confounding factors. These are the effect of the environment, it's the effect of genotype by environment interaction, and it's some random error, which might be a measurement error. Now, the good thing is that we can use field trials and that we can use field trial analysis to at least partially understand these factors and to remove them from our estimate of the genetic value that is based on the phenotype. So we can get an idea of how these factors affect our phenotype and remove it from our estimate. That's everything we want to achieve using field trials and field trial analysis. That's the key idea. Now, the nice thing is, with proper field trial designs and a proper analysis, we got the environment and genotype by environment interaction as kind of systematic confounding factors, at least to some degree. So we can correct for some environmental effects. This might be the effect of the location we're testing in, that might be the effect of the year, that might be things like a block effect, a row effect, column effect, all these kind of things. And we also can, to some extent, correct, but also use GxE interaction. And when we include this in our analysis, take care of it, the actual thing that remains confounding is the random error, but this one is reduced then. We can't get rid of that because this is the component that we don't understand. This might be very subtle differences in the soil based on different chemical compounds and whatever is there. But again, doing proper field trial designs and analysis, we can take care of some and get better estimates here, which means better selection decisions, more genetic gain, eventually what we want to get to. So let's look at these two components, what that actually means. The environment. The environment is probably, if I and you talk about the environment, we have different understandings of it because it's not a well-defined term. It can be a lot of things, and the environment is basically the non-genetic component, what you define to be the environment. It might include physical and chemical soil attributes, including those induced by soil tillage, crop cultivation, management in general, you name it, you do all this stuff, you know that. Obviously, climatic factors, precipitation, temperature, sunlight, drought, all these things that you encounter in the field. Unfortunately, we cannot control these. All kinds of biological organisms, and the measurement error. So again, there are some things we can control, some things we can't. By, for example, blocking, we can partially control for these attributes here. Climatic factors can be included in a year. So we can't change them, but we can include them in a year effect or in a location effect or in combination. So there's opportunities. Again, this cannot be controlled. This could be controlled, for example, not statistically, but using fungicides, using pesticides, using herbicides, whatever. So there are different ways to control that. Now, what does the environment do to our field trials? Basically can be summed as spatial and seasonal variation that we observe in our experimental fields. Now, let's assume we have the same exact location tested in 2 different years. Let's assume this is Dorcas' garden. Dorcas grows maize in her garden, and in the first year, well, we see in different colors here high and low soil fertility. There's like some diversity with regard to soil fertility, but in the next year, exactly same location, Dorcas did even a worse job putting fertilizer in the field, and there's a bigger area now with low soil fertility. So although we might think the same location is the same environment, it's not, and we need to take this into account. So all these factors that come together over the years have a, let's say, misleading effect on our selection. And this is, again, what we need to control for. Unfortunately, there's not only the effect of the environment per se on our genotypes, but there is GxE interaction. And, well, I see that often this term GxE interaction is sometimes slightly wrongly understood, so I want to go through a brief recap what it actually means. So let's assume we have the same genotype, the one that Dorcas grows in her garden, now in 3 different environments. We can measure performance here in these 3 different environments. We got 1 replication. And, well, how would you calculate the value of the genotype, the environment, and GxE interaction now? Any ideas? Well, the biometricians don't want to answer. The others, the hands never go up. Pardon?
What is the question?
How would you calculate the genetic, the environmental value, and the GxE interaction?
The same set of clones in different environments and experimental design, and we need to calculate the variance of the.
Well, this
is my traditional method. So,
it might be right. It's an overcomplication here. Basically, what we see is the performance of an individual in 3 different environments. So the value of the genotype, the genetic value, here is just the average of the 3 measurements across the whole TPE. This is the mean performance. This is the genetic value. The value of the environment is the value of all genotypes tested within that environment. So in this case, there is only 1 single genotype. So the value of the environment is similar to the measurement of this individual here. And GxE interaction cannot be calculated. There might be some, but we cannot statistically extract it, because to be able to do that, we need a second genotype, at least a second, rather more, to see if different genotypes behave differently in different environments. So what happens now? The genetic value of the yellow type here stays the same, because it's still tested in the same number of environments. If there was an environment 4 and we tested there, it would change. Now there's a second genetic value, which is the one of that orange, well, this time it's orange, last time it was purple, of this orange genotype here. Same idea, mean across all tested environments. The environmental values have changed, because now we're testing within these environments 2 genotypes. And the value of environment 1 is now the mean performance of these 2 individuals. We also can now calculate GxE interaction. And what GxE interaction actually means is is a difference in relative performance of the 2 genotypes across these 3 environments. So we can see that this individual is very good here and like doubles the size of the second individual. Here they're same the size, and here the ranking has changed. Though this is very clear GxE interaction, these individuals perform differently in different environments. And this is what makes breeding extremely hard for us. There might be some type of GxE, we're coming to that in a bit, which, as you can see in these 2, does change the relative performance, but not the ranking. In this case, it's not a problem, but this clearly is a problem, because we wouldn't know which individual to select here. What's important to remember here is that genetic value, the effect or the value of the environment, and GxE interaction are not kind of intrinsic values. They're nothing that is, I don't know, set in stone, carved in stone. They're statistical measurements, and they change regarding, or they change based on where you test your material and what kind of material you test. So they help you to make selections within certain TPEs, for example, but it's not that what you estimate is a fixed value. They're flexible. They're statistical properties. Now let's look at the different kinds of GxE interaction to get a bit better idea of what it actually means. We basically have non-crossover interaction or scaling, crossover interaction, or a combination of both. So I got 6 of these examples here. What we see here is, well, an axis that measures phenotypic performance in environment 1 and environment 2 of 2 genotypes. In this case, we see that in both environments, the genotypes have similar performance respectively, and they have the same distance in relative performance, which means there's a difference in the genetic value, but there's no effect of the environment because there's no change from one to the next environment, and there's no GxE interaction. What we see here now is still no GxE interaction because it's still the same relative difference, but the environment has an effect of the performance. So both individuals go up in their performance in environment 2, but it's still the same relative difference. So here we have no effects at all besides the genetic effect, and here we have an effect of the environment. Now, this might be something like a highly controlled lab trial or extremely well-controlled greenhouse trial in 2 locations. This might be something like testing 2 genotypes which have similar resistance in a location where there is no pathogen pressure at all, and then there's no pathogen pressure at all, and there is some pathogen pressure. Now we come to the complicated stuff, the one that is, well, these 2 are, for most traits, highly unrealistic. Unfortunately, what we see in the field, what we see in breeding is GxE interaction. And again, in the simple case, in the beneficial case, we have a difference in relative performance, a scaling, a non-crossover interaction, but no difference in ranking, which means genotype 1 is better in both environments. It's much better in environment 2 compared to environment 1, but still this would be the genotype of choice if we want to create or if we want to release a variety and put it into these 2 locations. No problem at all, easy to select, but again, mostly not the case. Unfortunately, the next 3 ones are what we generally discover. A change either only in ranking or a change in ranking and scaling. And this, again, makes it difficult because it means that if we develop a variety, the variety that we want in environment 2 is different from the variety that we want in environment 2. Did I say 2 here? 1 and 2. Now, to come to the end of GxE interaction, we cannot statistically solve this issue. We can identify which individuals perform better in which location, in which mega environment, in which regions whatsoever. But statistics cannot help you to change the fact that they behave differently. So what we can do now is define our target population of environments. Now we had a couple of discussions as well about this topic, and there are many different definitions. Again, I think there's no clear definition what the TPE actually is, how it is defined. The literature is often very confusing and gives you solutions to statistical problems, but not to practical problems. I like this definition, which is the set of farms and future seasons in which the varieties produced by a breeding program will be grown, right? It's very simple. You produce varieties for a farmer. You want the farmer to have success when he or she grows these varieties, though this is your TPE. Well, we had that discussion yesterday because Boja asked Eduardo this question, and I think it comes back to the same point. What does that mean? First of all, it means that we need to be clear about our target market, because the target market defines the product we want to generate. Then we can define or generate a breeding pipeline that delivers these products. And then after a couple of years, we might be able and check if within all these regions of our target market, if the genetics behave similarly or not. If they behave similarly, this is one TPE statistically. If they behave differently, we might need to split our TPE in 2 different TPEs to maximize the genetic output. It would still be the same target market, but it might be different growing conditions. So it's not only statistical questions, it starts again with your target that you want to achieve in the market, that you want to deliver to the farmer. And then when you collect the data, we can make data-based decisions. about our TPE. So, well, it includes environmental factors, obviously, because they affect the genetics, but it also includes these socio-economic factors, which then again mostly come back to the target market. So you could kind of think this defines the product that you want to generate, and these factors, these environmental factors, define which or how the genetics in this environment behave. And you have to combine these two factors to get a good TPE, but that's where you start, and that's what you try to optimize later. And this is basically the way to control or to use GxE interaction, because as I said, if you have a single pipeline for a certain market and you find out that in two regions there's very, very different GxE interaction, then you have to split. And coming back to that example, that's probably what after a couple of years you would decide to do here. So you have one big market for, I don't know, popcorn varieties. The same popcorn variety that provides popcorn for all the cinemas in the world. And well, in this environment, you see that the ranking is very different compared to this environment. So optimally, you would start having two different breeding pipelines that use the genetics you have differently, but you're still delivering to the same kind of market. You're just maximizing your gain by taking the genetics into account. Well, that's the brief introduction to genetic value, the effect of the environment and GxE interaction. Again, most important, it's a statistical property. It's something that depends on the environment and that will change over time, especially if we consider things like climate change, because the environment will change. Are there any questions about this so far? No questions?
So that will be TPE1, TPE2, that kind of thing.
Pardon?
So for example, the 2 and 3 can be TPE1 and E1 can be TPE2. So
exactly. So well, in practice it obviously gets even more complex, because this is what you observe statistically. Yeah. You see statistically that when you in TPE1 here select for the orange one, you make most gain, and here you select for the yellow one, you make the most gain. You will make more genetic gain than when you compare it to a single TPE, but there are other factors that come in, which is cost. Is the gain high enough that we get by splitting into two environments, TPEs, to justify a second breeding pipeline, a second, I don't know, bag of resources that you need, a second breeder, and all these things that you need to run a breeding program? Does it make sense, or would you, although you have a reduction in gain compared to two, stay in one single environment? It's probably, I would say, defining the TPE is, well, how do you call that? Like the most challenging question that we encounter in a plant breeding program. Yes, Boja, please. Can you use the microphone, please?
My question is about, we found different TPEs based on the data that we have. And do we need to have different pipelines in this case? For example, if we have very similar product profile, but the performance of the crop is different, there's interaction, right? So can we have a single pipeline and design our testing system, differently, and selection make differently, Can we do that within a single pipeline?
Sure. I don't think you can give a general answer here, but I'm sure this is an opportunity depending on how different the product profiles are. So if it's, I don't know, if you have a line program and for one of the lines you just want to introcress a different major gene at the end, and for the other you won't, then it's very obvious that one breeding pipeline with that additional introgression will do for the two markets. It's certainly an opportunity to consider when you make that plan, but I don't think there's a general answer to all these questions.
And maybe we should avoid, to always overcomplicate some situations. For example, let's start, as Christian said, thinking on one market segment. Let's think that actually that is the market segment that we want to cover. This is the entire region that we want to cover. This is the product profile that we're trying to cover, the popcorn part. And just after several years, you realize that basically that part probably is not being well attended. Environment 1, we're making selection, and mostly the selection is being, weighted by the environment 2 and 3, and the gain is going there. Basically, then the complex part really comes, but put the first part kind of simple, make sure that you have clarity on what are you trying to target, and then after several years you say, okay, let's create a new pipeline there if the cost, if all the things really justify that, that market will pay for it. Then you create that breeding pipeline for it. You completely split, these are 2 TPEs, 2 breeding pipelines, serving the same market segment, serving the same product profile. Because sometimes I feel like we come backwards and we say, I already have my big pipeline, I'm covering all the world, how do I do it? And then let's start in the right direction. Let's have the targets clear and see if...
yeah, exactly. No, I agree with you. But at the same time, can we make that, okay, in the beginning we thought like that's the same market segment, right? But later on, we figured out, okay, there is some interaction, maybe we should give a little bit more attention. So in this case, can we do, okay, make tier 3, tier 4 type of, segment, something like that? Is that possible?
No,
spillover effect, just give.
Yes, exactly. I think
if it is too small.
I think once you get to the cost part and you say, okay, we know that this is definitely not working well for all regions. We know that environment 1 really requires, special attention. Then after you look at the cost, then you can take the decision, okay, should we create an entire tier 1 breeding pipeline to serve this environment? Or can we just take, basically, well, almost first is to say we're going to abandon, environment 1. We focus on environment 2 and 3. Now the question is, with the resources and the efforts that we're putting in environment 2 and 3, do we just create an introgression pipeline to put products in environment 1? Or do we create an entire tier 1 pipeline to attend this market? What is really justified? Is the market going to, justify the $200,000, the $300,000, or the $1 million that we're going to invest in creating that breeding pipeline? So, yeah.
Yeah, something I also want to point out is, we see there's different components to the TPE. Let's say there's a market profile component, there's a genetic component, there's a cost component. There might be others, but these are 3 major components. We talk about how to statistically optimize this genetic component, but I sometimes got the feeling that the breeders approach us with a feeling that they're doing something completely wrong and we need to check that. I wouldn't say that. You've worked in different environments for a very long time. You have observed the performance in these environments, and you have probably a very good idea if the same genetic material behaves similarly or very different in different environments. You don't need a statistical analysis for that because you have a lot of experience. The statistical analysis can help and is important if you want to optimize it. But I wouldn't, at the moment, in your case, assume that you're doing something massively wrong at the moment. The environmental component, now this one is gone, the environmental component that you consider to define your TPE is probably already in a quite good shape. But what we also want to point out is that, we realize when the breeders approach us and ask, do we have a good TPE? They only think about the statistical component, but a lot of breeding programs do not have a market profile properly defined. And they don't have their breeding pipeline very well defined and structured. Though these are the 2 steps we need to do before we even think about the statistical point, because there's 2 major foundations of the statistical decision. that we need to make sure is in very well shape. So, well, this is a topic, again, I don't think this is very well covered in literature, and we had a lot of discussions to come to a strategy here, and we're not claiming this is the best strategy. We're coming with a suggestion here, and this is open for discussion. But we think it works pretty well in this way, and when you want to reconsider your TPE, it probably makes sense to first start with the market and then check if your breeding pipeline really serves that market. And when this is assured, we can look at the statistics. But starting from the statistics doesn't make a lot of sense. I need to use this one now because the battery is gone. Yes, Bert, please.
Yeah, I just had a question about, I mean, I like the definition of the TPEs you proposed, but I wonder, shouldn't like the field trials better mimic, for instance, the production system that is used in farms then? Because I don't know, I think that's not really the case now.
Yeah, of course. So the production system is in here in these, what I would call socioeconomic factors. So obviously, I don't know, in rice, for example, some breeders or some regions might prefer hybrids, others might prefer lines. You obviously can't deliver lines to those who prefer hybrids. But again, I think this fits into the market profile. Correct me if I'm wrong or if you meant something else, but I think this is part of it.
Yeah, I mean, for instance, maybe in the field trials we use fertilizer, but the farmers maybe don't have that.
Yeah.
So we do testing with fertilizer and then maybe...
This is another very important question. Do the field trials that we run actually represent our TPE?
Yeah, that's what I was trying to say.
The TPE is not our field trial. The TPE is the farmers, and the field trials we use, exactly as you said, might use fertilizers, and the farmers don't have access to fertilizers. So then we have optimized our testing system, but we have not optimized the genetic correlation between the experiments we run and the conditions that the farmers face. Boja.
Chris, may I?
Oh, thank you.
May I jump in this question? So, 1.5 years ago, Gary asked me to run some analysis for Beery, like a partner that we have from Bangladesh, and they have like a historical data set, almost like 20 years of like on-farm trials and research station trials, almost the same genotypes and some same structure. And the correlation is amazing, higher than 80%. So that's the good thing. So our research station trials has a good relation with these on-farm trials. So that's a good thing. Sometimes you think, oh, you are not like over applying something or like offering like a much better environment than in farms, but in fact, there's like a good trend, so more than 80–85%. So depending on the
thank you. Obviously, on-farm trials would be the optimal solution to that, but most of the CG breeding programs are not there yet, and it's not an opportunity. So considering the input or the management would be probably a better way to deal with that. Last question, please, before we move on.
When we perform the stability analysis, we try to control, well, we select the environments in the farm condition, but we try to standardize the fertilization, the plant protection, because the idea is to try to see if the clones is stable or no in different environments. And you said we need to try to minimize the error, environment error. So this is the idea of the TPA, but also you consider that we need to control all these variables in order to minimize the error in the stability analysis, right? This is correct, right?
Yep.
Or we need to adapt it to the condition to the farmers. If they planted without fertilizer, we don't use fertilizer. Another part use fertilizer, we use that. What is exactly?
Well, again, it depends on, like, to start with that, what we're showing you here is kind of the theoretical optimal solutions for everything. And we know that this doesn't always hold true in in practice, and that there are limitations to apply one-to-one what we're showing you here. So the optimal way would be you take the stuff that we're talking about, keep it in the back of your mind, but take it with a pinch of salt when you go to practice, and then try to find a good combination between what works practically well, but still does not ignore everything we're talking about. And it's still, in some programs, to some extent, this is happening, that it's completely the opposite, which, again, is not, like, I'm not blaming anyone. We know that in the CG over many, many years there have been programs inherited and so on. Also, again, in the literature, these things are not very well covered. Again, we're not trying to blame anyone. We're trying to make you question what you're doing, make a couple of steps back and decide, am I actually following these guidelines or not? And if not, reach out to us and ask us to make it better. So now coming to your question. Well, again, it depends. Obviously, you're producing varieties for the farmers, which means you want to find those genotypes which work best in the farmer's field. And if you have highly controlled experiments with fertilizer, with herbicides, with perfect management, and the farmers don't, then the trialing you do might not be the best to represent the farmers. But to be honest, I don't have a good solution for that at the moment. Eduardo already has his mic. He's probably want to comment on that as well, but it's a very difficult question.
No, yeah, I agree with everything that Christian just said. I guess I just want to add that I guess when it comes to deciding how the environments for the trial looks like, you need to understand, I guess, how the farmers work, you know, under what conditions they are. And I know that you do. I mean, you know that the farmers are in drought conditions or low fertility or high fertility, optimal. And then you basically have to figure out the two options is, like Christian said, you send your trials to the same conditions on the own farm, or you just mimic those environments depending on the level of resources. You take one or the other decision. That doesn't mean that if, for example, if the grower doesn't apply fertilizer or goes under drought, that you just basically put your genotypes in one field and you forget about it, right? I mean, it means that you have to mimic drought, but carefully, right? I mean, you have to basically control the environment, just keep levels of irrigation. I mean, do a very well-managed environment. Doesn't mean that because the grower grows in very bad conditions, we just put our trials in very bad conditions. So I guess just the answer to don't make it go that far, as Christian said. I mean, it's complex, but in general, you characterize the TPE, you understand how it looks like. If you can go to the TPE, you go directly to the TPE. If you cannot go directly to the TPE, you create environments that look like the TPE.
I want to move on because this is not the actual topic. We can discuss this.
Yes, let's. Yeah, no, I would say.
No, I need to be strict here. Sorry,
yep.
Mokhtar. Yep. We can discuss this in the coffee break, Maria as well. But TPE definition anyway, the master class. And to be honest, most of the programs are not at the point where we should be too bothered about statistical redefinition of our TPEs. They are low-hanging fruits and easier ways to improve our field trialing, and that's what we're going to look at now.
But Eduardo said very interesting because we don't define very well the TPS. It is very important key because after we need to recreate.
Sure, but what you should do now is define your market profiles properly and then check if your breeding pipelines provide that. Now, if we come to the last point again, the statistical analysis, if your breeding trials are not in good shape, the statistical analysis is pointless as well. So what we're looking at now is like basic factors, how to make sure your field trialing is good enough to have the proper data to go in a few years to the statistical analysis of the TPE. You have these two major points that you hopefully take home and check markets and the pipeline manager or your pipeline in general. This is how we create the foundation to do the statistical analysis in a couple of years when we have enough data. Now, field trials or field trial designs, analysis of field trials, I said that are to control for confounding factors. And again, we need to make sure these confounding factors are controlled well enough so we got a good representation of our locations so we can go to the TPE analysis. How do we do that? Field trials. I just want to make a quick point here. So a concept we normally, or we often use when we talk about field trialing and the different stages is we talk about early stage trials and late stage trials. This is not very well defined, but every breeder has, for his or her breeding program, a good idea what that means. And I think we can continue talking about this early and late stage trials, but what I also want to do, or what we in general try to do here with you, is make you reconsider and question the concept that have been around for the last 50 years, because they have been around for the last 50 years. Very little has happened in plant breeding within this long period. In, I don't know, chemistry or quantum physics, no one would go back 50 years and use a theory that has been established at that time. It's long, long outdated, and we still stick to that. And, well, again, Eduardo said that we're not going to tell you here what to do, but we want to hopefully help you question some of the things, reconsider them in your breeding program, and then if you want to change something, come back to us. So early stage, late stage. Normally our understanding is kind of early stages means few replications or no replications at all because we have limited material. We go to one location, again, because we have limited material, and we get little information. Later stages, and we have a lot of individuals. In later stages, however, we have done some selection. We go to many environments or locations. We have less genotypes, but we replicate them quite often to make sure we get good information. And there's nothing wrong with that, but that's not the whole truth. Because with number 2 locations, regardless if it's early or late stage, you could go to a single, but you also could go to multiple locations. Optimally, you manage to test all genotypes in all environments. But at early stages, that's obviously not possible. Sparse testing, however, which basically just means not testing all individuals in all environments, but having different sets of genotypes in different environments, would even allow you to go to many locations in an early stage. We will see later we need a genomic relationship matrix for that. But it's not carved in stone that early stage means low number of locations. You can go to more locations, and that again will be better to get an idea of your TPE that you sample. The same holds a bit for the within location design. So, well, we can think about these designs. Again, the alpha lattice, RCBD, P-reps, different sparse testing designs, row column designs, whatever. We can classify them into fully replicated, partially replicated, or unreplicated, like an augmented design would be. Well, if we have very little material here, we obviously cannot do fully replicated. But the idea that later stages have to be fully replicated also is not the whole true story. In later stages, we could go to unreplicated or even sparsely unreplicated designs and increase the number of locations we're testing in. We don't have to test 3 or 4 replications in later stages per location. We can spread it. And we're coming to that point. But just to let you know already that this, as we often conceive it, is not necessarily what we have to do to have good field trial designs. Sparse testing just means, imagine you in an early stage and you have 1,000 genotypes that you want to test, but only 1 replication or 1 individual per genotype. Sparse testing means, for example, instead of testing 1,000 in one location, you test 500 in location 1 and 500 in location 2. And by using a genomic relationship matrix, again, this is key, you can connect these individuals and you get information from more locations, from the genetics in more locations. There's no benefit if you don't use the genomic relationship matrix /GRM, but if you have it, you can go even to 4 locations and test 250 in 4 locations. So early stage testing is not limited to a single or very few locations. You can increase it there. There's some basic that need to be fulfilled, but then you can go to more locations. But we'll come to that later. I have a figure that comes later. Now, why are we all doing this? Famous quote by Fisher, to consult the statistician after an experiment is finished is often merely to ask him to conduct a post-mortem examination. You can perhaps say what the experiment died of. So what we want to do now is give you some of the key basics that are not too complicated to make sure if you pass on your data to the biometrician, he's not in this situation. So he has proper experimental data and can do a good analysis. It's important also again to point out here, well, the literature often suggests that the statistics define how we have to run our field trials. But that's not entirely true because there's obviously a difference between academia and the practical world we're living in. So there are some statistical rules we need to respect, that if we work within these rules and we come to that, replication, randomization, and blocking, then your biometrician, or if you have to run it yourself, you're normally in a good situation to extract good and useful data from that. But you should stick to these. And when you think about all these different field designs we're using, I guess alpha, lattice, and RCBD are probably the most popular within the CG programs. In the later stages, in the early stages, you will have to do an augmented or a p-rep design or something like that. But what all of these designs do is they use these 3 principles in different ways to optimize the quality of the data we can extract, to correct for spatial and temporal variation. Now, replication is necessary to get an estimate of the error. If you have your genotypes not replicated, you can't estimate how well their phenotype represents the genotype. So in an augmented design, we need a couple of something like checks replicated to get an estimate of the error. But it also reduces the error. Very basic statistics, your error over the number of replications, and if you have more replications, your estimate gets closer to the mean and gets better. Randomization is necessary for the validity of the error, but it's probably the most important factor that you see here. I had a discussion yesterday with Xiao Fei, and you said that you still put the families together. And again, we have to respect here that sometimes there are limitations in practice, and that complete randomization might not be feasible for you because, I don't know, because of the resources you don't have, I don't know, whatever might be the reason. But it's not the best practice. So if you can randomize and if you have families and put them together, one option might be you split your family into 3 blocks of the family and put them in different plots. Yes. Then you have at least some kind of randomization to that. The idea is very important, and I need to go a couple of slides back. Imagine you compare 2 families, and one family that is really good is here, and another family that is mediocre is here. You're going to select this family because the conditions here are much better. But if you put half the family here and half the family here, you get a better estimate. So randomization is key to control for this. Statistics help you to control for this, but your statistics are going to fail if you don't provide the key principles of experimental designs. Very important, randomization makes sure that the genetics are distributed randomly across this heterogeneity within your field. Exactly.
Yeah. This is very common to practice, to put families together.
Yeah,
Exactly.
We have been doing for the last 60 years. We had been doing.
Yeah. And, well, this is, when you go back to the old Fisher papers, which were like 1925, he already criticized the agronomists back in the Rothamsted Institute that they don't randomize. And 100 years later, we're still there. So it's very important. And the funny thing is, basically, since 1925, for the last 100 years, these principles have not changed. They are still valid. And they still guide every new method of field trialing that we come up with. It's all based on this. The last thing is blocking. And, well, I need to go back here as well to show you what blocking does. So this was especially important in the old ANOVA way we did trials. So we would have, for example, 4 subblocks here, one vertically lined, one horizontal line, and we have 4 subblocks. And we did that because the subblocks are more homogeneous than the whole entire testing block. So blocking helps to reduce the error because the conditions within the block are more comparable. Now we will see then that when we come to linear mixed models a bit, that this idea of sub-blocking as we used to do it in the ANOVA times are not, or is not that important anymore. We don't need to create subblocks anymore. The mixed linear model, well, you can put in row effects, column effects as random effects. We will come to that. And this is a kind of blocking. Your rows and your columns are now a block. But in the ANOVA model, you couldn't properly estimate these rows and columns. With the linear mixed models, you can now. So the classical idea of blocking we have about subblocks becomes a bit redundant. But blocking is still very important. It's just approached in a different way, and we will see that. But this is the most important thing you need to remember, and that's everything you need to know with regard to METs and with regard to within trial designs. Randomization, replication, blocking, that's the whole magic. If you do that, give your data to your analyst, and he'll do a good job. Now, I said that. This is another important point I want to make. When we talk about replications, we normally talk about replications within environments, right? We say, okay, we have location in Dorcas Garden, we want to make an experiment there, and we replicate our individuals 3 times there, which gives us 3 randomized complete blocks. However, putting blocks into different environments is also replication. It replicates the individuals within your TPE, and that's what you're breeding for. You're not breeding for Dorcas Garden, you're breeding for whole Kenya. So putting... Okay. Sorry, Dorcas. So anyways, a single location is only one sample from your TPE, but you want to cover the whole TPE as much as possible. So what would you do? This is obviously North America. If you have 5 plots for a single genotype, would you test them like this, or would you test them like this? Exactly. I think this is very obvious because this does not sample your TPE. You get a very good idea of how your individual performs within this location, but this location is not your TPE. This is your TPE. And this is already the answer to should we test in more locations or should we test more replications within locations? Go to as many locations as possible because it samples your TPE well. It samples the region well that you are breeding for. Now, that's a simple answer. That's the key message. We're going to look into the details a bit, what that actually means. This is a second equation. This is the broad sense heritability or repeatability, which basically means if you put, if you have 10 plots and you put them in 10 locations, You select for the mean how representative of the genetic value is the mean of the phenotype. It's quality. So the word heritability or the term heritability is another of these very, very confusing terms because it has many, many different meanings. If I talk about heritability, it's probably different from your understanding of heritability. Instead of trying to narrow down the understanding of heritability, people have over the years just added new ideas of heritability, and no one knows what's going on anymore. Again, something that if you do that in quantum physics, or if you do that in physics and try to shoot a rocket to the moon, it would explode because people are talking about different things. That's actually what happened, I think, with the Challenger. Some people, they were talking about measurements. Some of the scientists were thinking in the metric system, the others were thinking in inches. Therefore, calculations went wrong, and the Challenger exploded. Well, we're not in that danger in plant breeding programs. The only thing that's a danger is your job, so be very careful. Well, anyways, we already have our answer here. What improves the quality of our field trials? We have two factors that confound our genetic estimates. One of them is GxE interaction, which is controlled by going to more environments, and one is the error, which is controlled by the number of the environments and the number of replications. So if we increase the number of replications per environment now, this is what we reduce. If we increase the number of environments that we test, we reduce this and we reduce this. So very easy again to get a good estimate of the genetic performance within our TPE. This is what we want to increase. And again, it's important, not only this is a replication, this is a replication as well. This is a replication within your location, and this is a replication within your TPE. And this is what you try to sample. So try to maximize this. This is a simple deterministic answer. Marley talked this morning about that there are a lot of assumptions coming with these deterministic models. They're valuable, but running simulations, for example, has a couple of benefits. And one of these is that you can check different scenarios. Now what we did here is we simulated a TPE that consisted of 600 farms. These are not the 600 farms, this is just an excerpt. But we simulated 600 farms. And we assumed different genetic correlations between that farms, which basically means if the genetic correlation between the farms is high, our individuals will show same or similar performance at all farms. If the genetic correlation can be low, you will see there's some white here, which means the correlation between this farm and this farm here is very low. So the yield that we observe in farm 1 will be very different from the yield that we observe in farm 2, and the ranking will change. So that's basically, again, what happens. This means high genetic correlation between farms means low GxE. Let's see that here. Low GxE, and there's some difference in relative performance, but not in ranking. If we go down to low genetic correlations, that means the performance between farms differs a lot, and there will be re-ranking. That's basically what you see here. Here, there's a correlation between the performance, a high correlation between performance in environment 1 and 2. And if you select these individuals, they will perform very well in both environments. And here, there's no detectable correlation. It's just like a round, circle-like cloud of all the performances. And when you select this individual, which is really good in environment 1, it will be really bad in environment 2. So what does that mean for our selection? What does that mean for going to different number of locations? That's shown here, and there's a lot of information on this slide. So please try to bear with me while I explain stepwisely what's happening. So we assumed we have 600 individuals in total, and for each individual we can plant 20 plots. Now what do we do with these 20 plots? We, for example, could go to 2 environments and plant 10 plots in each of the 2 environments. We could go to 10 environments and plant 2 plots of each individual in the 10 environments, or something in between. Now, these are the genetic correlations between the farms that were covered, going from very low to very high, up to, well, a relatively good high genetic correlation between the different farms. We got the repeatability, again, the broad sense heritability of our experiments here on this axis, and here we have 3 different types of heritability per plot. So the information we collect per plot can either be quite bad, which probably would be something like yield, or really good, which might be disease resistance in a highly affected area. Now, we see a couple of things. The first is, this means there is a lot of GxE. Our TPE is statistically not well defined. Again, this is what we see. You don't know which variety to select because the varieties perform different in different environments. Not well-defined TPE. And what we see is, well, if we increase the number of locations, there is an increase. But there is a slight increase, and in general, the heritability or the repeatability is quite low, is quite bad. Why is that the case? Because across all these environments, we're collecting contradictory information and we don't really know what to select for. This is, well, this is not a statistical issue. This is, your TPE is not well defined. Again, this is probably not where you're in. You have observed your material over many years and have a good idea of how it performs. If this is the situation you're in, and you don't see it in the field, then you're probably not a good breeder, but I doubt that that holds true for any one of you. These are the other situations, which are probably a bit more realistic. That might still be a bit too low. This might become more realistic. So what do we see now? We see for all different scenarios that if we increase the number of environments and reduce, therefore, the number of replications within an environment, we have an increase in heritability. Of course, when the genetic correlations between the farms get higher, our accuracy also gets higher because we're collecting from different farms very representative information. But regardless of the genetic correlations, it's always better to sample more environments. Again, you see that the trends are slightly different. So when one environment is already very representative of the others, the increase is a bit lower. When the environments might not be very representative, but not as bad as here, going to more environments pays off a bit more, but again, it always pays off.
Chris, it's an entry-level heritability or plot level?
It's plot level heritability, which means well, what we did is we simulated different number of plots. The phenotype that you observe in a single plot is 0.2, 0.5, or 0.8 accurate. And then obviously when you combine 10 plots within 2 environments, for example, you get the entry mean. But this is the heritability that you observe per plot.
And Bauja, maybe just to add, in this case, look at the y-axis where it says repeatability, kind of the accuracy of the selection. So somehow think on the breeder's equation, think that the response variable here is the accuracy, and the simulated part, that this is the part that we do not control in the simulation. Like basically Christian will find different results for this response variable. Yeah. What he's controlling is the x-axis, the actual plot level heritability. So.
Yeah, thanks for pointing out. That's important. That's what we control. That's what we define. And based on the heritability that we set for a plot and based on the number of environments and replications, this is the broad sense heritability we actually achieve. And again, there's a bit more stuff in here. It's very complex. But are there any questions on this, or is this clear?
Yeah, but I'm still not quite clear what's the plot level heritability. Is within trial or is...
Plot level just means, imagine you put one single plot in your garden and you're going to evaluate it. How accurate is this plot? This plot might have a 0.2 heritability, which means the phenotype you observe is not very representative of your genotypic value. There's a lot of error, and this means the opposite. But this refers to one single plot that you put in the field. So it's just how accurate is the information that I get when I evaluate a single plot. Yeah, and then you combine the information from different plots, and you get this heritability, this repeatability or broad sense heritability. Again, the issue here is heritability has different meanings. One heritability is used to calculate another heritability, or not to calculate it, but affects another heritability, which is also called the repeatability. But plot level just means a single plot, how accurate is the information in that single plot? How representative is that phenotype of the genotype, and how much error is there?
I understand, but only I lose about that. The genotypic correlation is as numbers, the different numbers in the tops. How you determine it? Only.
What do you mean? How?
What kind of information you use in order to determine that genotypic correlation?
Well, what we do in the simulations is we simulate. Let's say we simulate an organism like rice with 10 chromosomes. Within these 10 chromosomes, there are a couple of alleles. We assign an effect to these alleles. And the effect of the alleles in this environment here are negatively correlated with the effects of the alleles in this environment. So this is basically just what leads to re-ranking. This wasn't well explained. I see that from your facial expression.
I think it's saying that one genotype is not performing the same in one environment as in the other. So
Let me.
See a correlation that can be high, it performs the same, or low,
Yes, Elisa, and we simulate that because that happens in reality, right? I mean, you have some genotypes, and if you put them in two farms, and the farms have very similar conditions, they might behave the same. But they could also be, you know, in different conditions, and sometimes they don't follow this linear trend, but just because the farm is better, they increase linearly. Sometimes it happens that just some of those conditions make the genotypes to behave completely different, to change in ranks. So in the simulation, basically, we force those correlations to exist. So basically, we simulate, let's say, that the alleles have certain G by E interaction in a way that when we observe these 100 individuals in a farm and the same 100 individuals in another farm, they show those levels of genetic correlation. So we can simulate that they have a high genetic correlation, or they have a low genetic correlation. But basically what Christian is simulating here is not just one value, he's simulating a range of values. So he's simulating a distribution of genetic correlations. So in the first square, the -0.9 to 0.9, he's simulating that there is an entire distribution of genetic correlations that extends from the very negative to the very positive. What it means is that the TPE is too broad. Probably it's like trying to simulate that you're trying to breed for the entire world. So you will see all possible genetic correlations. In the other corner, 0.6 to 0.9, it means that the genetic correlations are relatively consistent. There is a distribution. There is actually values that go beyond and below these values, but on average, this is what is capturing most of the distribution. It means that, in general, you're finding more or less the same values. It's like saying, okay, I'm only breeding for this country, or I'm only breeding for this particular region. Christian?
So imagine you have two farms, farm 1 and farm 2, and you're testing two genotypes on these farms. So when we look at the first genotype shows a high performance on farm 1 and a high performance on farm 2. These are two different environments. So the genetic correlation between these two environments is very, very high because they show similar performance. It also means if you test in the environment on farm 1, you don't have to test on farm 2 because this information is enough. You get the same information here. Now the second genotype shows high performance on the first farm, but very low performance on the second farm. This means in 2 environments, they show very different performance, and therefore the genetic correlation between these environments is very low. So again, this example here would lead to something like this, where the performance of genotypes is relatively simple across 2 environments, and this is what you observe here, where the genetic correlation between the environments is so low that you observe very, very different performance, and that's what genetic correlation is. And so when we simulated that, we simulated not 2, but 500 or 600 farms, and these 600 farms covered a range between very, very high and very, very low and everything in between, like in your actual TPE, and then sampled some of them and checked how representative are they for the whole region. So you might sample this, and this farm and want to predict the performance in the whole TPE.
It's clear to me, but I understand that this is the ideal life, right? This is difficult to find. Yeah. It's only a simulation because it depends on the traits,
Well, normally when we are thinking on this, we are thinking on traits that are GxE, like yield, right? We are not thinking, or we don't define TPEs based on simple traits. We normally define TPEs based on complex traits like yield. And what we normally observe, even in your data sets that we have analyzed with you, is normally more in the situation that you are in this third column, like, something in between the last 2. Normally what we have observed is that your mean genetic correlation is like 0.5, and it goes to 0, and it goes to 0.8. So it's a wide distribution, but it's more or less on this right side area.
You got another question, Rosa?
Yes. Is genetic correlation related to stability?
Yes. So that actually is what it is. If the genetic correlation of a genotype, of environments for a genotype is high, you observe something like that is very stable. If it is low, you will see something like this. So stability is a good way to think about it. Boja, please. Quick question, very quick.
Just practical question.
I'm not a practitioner. I'm a theoretical guy.
No. Recently, we got data from our partner, from one country. I'll not tell which one is that, and then they put their experiments across the country, 22 environments. They are national trials, and they got the data from 25 varieties, advanced lines, and they put them together. They got the mean, and they selected based on that one. But it turned out, I look at the data, and then try to classify those environments, and I saw the range of genetic correlation is all the way from minus 0.5 to plus 0.5, or 0.6, something like that. So
okay, yeah, that's
a big problem, right?
That's the very last important point here to make. Well, you don't see that here, but it depends on the time range of the data. So if you look in a single year and you compare 5 locations, no, let's look at that differently, which, again, let's go back. This is actually a better example. Let's look at this. This is the same location in 2 different years. And if you look at the same location in 2 different years, depending on the years, it might have a really, really high or really low genetic correlation. In one year, it might be very, very, very dry. In the next year, there might be a lot of rain. And you have 2 very different conditions in exactly the same location. So if you only look at these 2 years, your impression might be the genetic correlation between these environments is negative. That doesn't make any sense. Well, that's why you don't look at a single year or only 2 years, but you need to look at many years to calculate an average. Now, in this example, this probably is obvious. It's a bit more complex, but also not too complex if you think about different environments. So what happens if you sample of the environment I showed you, if you sample 5 or 6 of them? Now you have a region that you define a TPE, but just by chance the weather is very different in these 5 regions. Then you will get something like this. But this is not representative of your TPE, because the TPE is a multi-year product of your environment. And that means if you collect data over 6, 7, 8 years and then calculate the genetic correlations, you might within 1 year end up here, and over many years you will end up here.
Yeah. No, I think the problem is like not defining TPEs, because in many countries they don't do that, right? They just gather the data and get the average and decide. You know.
Okay, yeah. I mean,
still that is practice like
this
that.
might be a problem, but that's again comes back to why I said you need a couple of years of data to do the statistical analysis, because one single year just due to the weather in a year might give you this. What you're interested in actually is a multi-year effect of an environment and how they are correlated. So if you have multiple years of data and try to calculate genetic correlations and you still end up here, then this is an issue.
Got the point.
And maybe just a comment, especially because the biometricians analyze this data and they observe these patterns. It's actually more common for them to observe that in 1 year it looks very good, like 0.6 to 0.9, or let's say 0.4 to 0.9. And then if they put 2 years together and they analyze it, then they start to see these extreme ranges to minus 0.2, a couple of locations that they don't match anymore. But that's totally okay, because like Christian said, the year effect creates all these artifacts. So even though you want more years of data to come up with decisions, that doesn't mean that you're going to just make an analysis with all the years together and assume that that is the total range. I mean, it's like, I mean, you do the analysis together, but somehow you kind of also look at the year-by-year picture. Because of course, over 10 years, you may find some of those extreme values that, and you would think, oh, then this location, Kenya 2014, doesn't fit at all. Should we just remove Kenya? No, but Kenya in 2020 and 2018, it fit perfectly. So it's not as easy as just looking for, those extreme values that don't fit in the genetic correlation matrix and say, oh, these countries don't belong. No. I mean, it's a bit more sophisticated than that. But I guess let's not get into the very technical details. But what Christian said is it's important that we need multiple years of data to create a good understanding of how the TPE behaves.
Yes, please. Bert first, then Xiaofei, and then we move on because we're running out of time. Yeah, very quick, 2 questions.
I just wanted to comment that often if we say to use more locations or environments, that then we get a response that it's logistically more difficult and also more expensive.
I'll come to that, because that's a very important criticism. Again, first we're talking about the statistical optimal properties, then we're going to look at the practice a bit.
Yeah, great point, Bert. Yeah.
Yeah, so my question is, can we compare the 0.5 with 0.8? So the reason is if we have, we have certain amount of Cs. So if we have multiple locations, so we can have smaller plot size, right? So that means the plot level heritability might be lower than the original one. So can we compare 0.5? I mean, in this figure, or
no, we can't compare this in the figure, because if we trace that back to the plot size, this would mean that 0.2 of a smaller plot would also have more plots. So what we're doing here is just, assume it's different traits. This is a trait, this is the same plot, but it's a trait like yield, which is hard to evaluate on a single plot, and this might be a yield like, I don't know, resistance that is easier to assess in a single plot. But if you want to increase the number of plots by reducing the plot size, then these numbers would have to change.
Okay.
But it is a way to do that, actually, to go to more environments, for example, by reducing the plot size.
Yeah.
Now, let's move on.
Thank you.
Because the next question would then be, well, if we have to increase the number of environments to get a better estimate, how many environments should we go to, right? We get the same kind of figure here. We get, again, the same range of genetic correlations for our 600 farms. We get the same plot level heritabilities, and we're measuring repeatability within our whole TPE. What we change now is the number of locations that is tested, or environments, and we're going from 1 to 30 environments. Now, to make that quick here, this again shows us it's not a well-defined TPE, and even if we increase the number of environments further and further, we're not getting a good repeatability because the information we combine is not to be combined. More interesting are the other three ones. And we see that that is again what you can derive already from this equation. With the number of environments increasing, these two components are reduced. But you know that when you divide them by 2, there's a huge effect. And when you go from 2 to 3, there's still a good effect. But if you go from 100 to 101 environments, the effect becomes marginal. The error is not reduced a lot anymore. And now the question is, what's a good number to reduce the error? Now we observe in these simulations, we observe these plateaus. And we see that, well, if we go into these ranges of medium to high genetic correlations, we see that, well, we see that everywhere. At the beginning, we have a huge increase. And then the more we increase our number of environments, the more it plateaus, and at some point, like, there's very, very little benefit. So, well, what now holds true for your breeding program has to be decided based on your data. But I think you can derive 2 kind of rule of thumbs here that you could take home with. The first one is when you're at a very low number of environments, going to even 1 more or 2 more environments has a tremendous effect. And that comes back to Bert's comment. Well, when we're here, we won't be able to go to here because we don't have the resources. But if we are here and the breeders tell us, well, it's too expensive, we can't go to more, try to convince them to maybe go to 1 more environment, because the costs that comes with are, well, they're not massive, but the increase in accuracy, which then again turns into selection gain, is massive. So at these numbers of environments we're testing in within our TPE, it really, really heavily pays off. So if you go further and further, I would, again, rule of thumbish say that at something like 15, especially when you see this genetic correlations, which I would say is probably over time realistic, if you go to something like 15, it becomes quite marginal. And it probably does not economically pay off anymore. It will always statistically pay off, but the extra costs that come with an extra environment are probably not justifiable. So if you're over 15 and you can afford that, very, very good. But if you go into the, let's say, in the cost analysis of your breeding program, going from 20 back to 15 might maybe give you some money to use somewhere else. This gets very complex. This is something we cannot answer based on only statistics, quantitative genetics. This is a very complex analysis of your breeding program. But again, the key message, a low number, if you're in a low number, try to go to even only 1 or maybe more, 2 more environments, because this is where you get a huge extra gain, where you get a good increase in your selection accuracy to improve your population.
That is within
This is within the same TPE. That's important. And again, if you observe something like that within the same TPE, it's not a well-defined TPE. Question?
Yeah, but still there is some gain, right, in that one? Undefined, not properly defined TPE as well, a little bit? This is what like some partners are doing. That's, I mean,
you mean
they're just combining whole data from the country and then making the decision. That's my point.
Yeah, well, I mean, there is some gain,
right?
There is probably some gain, but it's very simply you have a huge TPE and you're selecting the best individual for there will always be a best individual for that whole TPE, but it will not perform equally well in the different populations. So over, let's say you do that for 10 years, you could either have, we will go back here. Well, what do we have here? We have our genetic gain and time. This is time, this is delta G, and well, you have one TPE here, and you might have two TPE here. TPE1, TPE2. So what would happen is, when you select for one single genotype, for the best genotype in a badly defined TPE, you still would make some gain for this genotype 1, but it won't be high. But if you then split this TPE, this not very well-defined TPE, into two and select for different genetics, what will happen is here you make good gain with genotype 1, and here you make good gain with genotype 2. Again, it becomes an economic question. This cannot be answered. Just because you make more gain here does not necessarily mean you're making more economical gain, you're earning more money or whatever your target is. Your target is not, well, the donor's target is gain, but your target might not necessarily be pure gain, it might be economic gain. So it doesn't mean that this is the economically worth decision. But with regard to gain, it would make sense to go to two instead of one single environment, because you can find adapted material for the two TPEs instead of a genotype for one TPE that is not able to serve all the different locations. Okay, so these are just the guidelines summed up if you want to go back to the presentation, so we can quickly skip that. Low number of locations, there's a high increase when only one extra location is added. High number of locations, low to marginal increase, so the money might be better used somewhere else. If you have a TPE that contains locations with moderate to highly negative genetic correlations, more locations only show a slow increase because of what I showed here. And this might indicate your TPE is not well defined, so going to more locations is not the solution, but splitting your location. Number of locations. Well, this is where now the practical component again comes in. If the resources can be freely allocated, maximize or optimize the number of locations and reduce the number of replications per locations. That is what we did here. You have a fixed set of plots that you can put in the field. Optimally, you go here. You go to as many locations as possible and reduce the number of replications within. However, again, we know this is not always possible. You probably won't be able to go from 2 to 10 locations, at least not within 1 or 2 years. But in that case, maybe try to go from this to this one, because this is where you get a lot of benefit. But also very important, we're talking about reshuffling your resources. A fixed set of plots, and instead of staying in 2 locations, you go to 4 now and redistribute the plots. The message is not, and that's very important, do not reduce the number of replications within environment if you can't go to more environments. because every replication, even within environment, is good extra information. There's a limit to that, because within environments, more than 4 hardly pays off. There's again this plateau of accuracy we get within a single location. So even if you have 20 plots and you want to go to 2 environments instead of 1, don't put 10 in there. That doesn't pay off. If you maximally can go to 2 environments, and you could go for 10 replications per environment, that's not a good decision. Use these resources somewhere else. 4 is where it starts to heavily plateau. We will see that on Friday. So again, very important, don't reduce the number of replications within locations if you can't go to more locations. Now again, I said that if the number of test locations is low, try to increase. If it's already high, your resources may be better used somewhere else. We talked about all that. It's, again, the key messages that you get from these figures, because there's a lot more information in there, but it's summed up here what you should take with you as a take-home message. So these were, let's say, the cross-location designs, MET designs. How do we deal, what the design with regard to the number of locations? Now we have said that, and we're interested now, what is the best design within each of these locations? And that again is alpha lattice, RCBD, all the things that I mentioned before already. Which is the best design? Very popular question when we talk to the breeders. The very short answer is they're kind of all the same if you stick with the design. Again, if you do replication optimally across environments, but very important within environments, randomization and blocking. Randomization cannot be discussed, must not be discussed. Blocking is done in the mixed models framework when you collect row and column information. So what's important to optimize the within location designs in your situation? Well, this is what probably is representative of a conventional toy example, and there's nothing really wrong with that. In early stages, again, the material is limited. We're doing an augmented design in 1, maybe 2 locations. Later, we might do something like a P-rep because we have a bit more material, and the more we increase the material per genotype and reduce our tested genotypes, to more locations we go and more replications within locations we have. So again, this is a robust approach. But the question now was, how do we optimize this? And I would say the answer to this is a good within location design serves a good across location design. So again, I would try to optimize it in a way that I can go to even more locations. And let's look at how this might work. So we have 1, 2, 3, 4, 5 different kind of designs shown here. These rows are the number of test locations. We got 12 rows, which means 12 possible test locations we could go to. And this is the number of replications per genotype indicated by the color. So what we have here is 1, 2, 3, and so on to 10. It's 10 genotypes tested at 3 replications in 2 environments. Now if we reshuffle that, and again, I know there's extra costs coming with going to more test locations, but we're not changing the amount of resources with regard to plots. So what could we do? We could go from 3 to 2 replications per environment, and we can already go to 3 environments. We have 1 extra environment. We could do something like a P-rep, which means 50% of our individuals per location are replicated, and with the same resources we can go to 4 locations. Now again, augmented designs, only 1 replication, and we can go to 6. So it's the same amount of resources we're using, but we're doing better here sampling the TPE. And that's what I meant, that even in early stages, you could go to more environments by just sticking with an augmented design or with one replication and distributing it to more locations. Now this is when we still consider the individual as a replication unit. Now we're coming to sparse testing, which is again the most complex way to approach that, but it gives us a lot of opportunities. So if we now only put 50% of our set, which means not 10, but only 5 individuals in each environment, we can go to 12 environments instead of 2 where we started from. So this is a tremendous increase. I said that before, and we're going to get to that. This requires a genomic relationship matrix, because this individual is not tested here, and this individual is not tested here. To connect these and to figure out how this would perform here, we need the genomic information to combine this. So this is highly complex, but I said that also before, it doesn't have to be complex. Even with very easy, simple measurements, or measures, not measurements, you can go from this to this and you don't need a GRM. You don't need to change the approach you're breeding. You just need to find a couple of extra environments, reduce the number of replications, put them into like environment replications rather than replications within environment, and you get a good extra gain, a good amount of extra gain by sampling your TPE better. The second way, again, to improve your within location design, and I said that before, is again that randomization, replication, blocking. So there are different, many different designs. We compared some of them. There's a paper out there, I'm going to go there first, which compares different designs. We didn't simulate that. We put it in the Dropbox folder. It's worth reading. It wasn't, well, Eduardo is on it. It wasn't their major message. So sometimes you now and then have to read between the lines, but basically this is what turns out. When you use a linear mixed model, as I said before, the designs all kind of become the same, achieve the same performance. If you still consider replication, randomization, and blocking. Now, why is that? And I'm going back to the old ANOVA example, how we all learned that. In the ANOVA days, we would create these subblocks within a whole block, because again, you can see this, these field effects or these environmental effects here are very similar, the ones here are very similar, but if you consider a whole block, there's a lot of variation. So we want to estimate an effect of a block and then correct the individuals within that block for the fact that there might be a block benefit and a block disadvantage. Now to do that, back then we needed the same checks in these subblocks to compare them, to figure out that this check shows negative performance here compared to the mean, shows positive performance here, and correct our individuals. We wouldn't only need one single check, but we would put a lot of checks in there and different check genotypes to get an estimate of the block effect. And well, with ANOVA design, that was necessary because there was no other way, no other good way to correct for these field effects. That was a good approach, but this approach is, well, has been outdated now for 20 years. And mixed models, again, still kind of do the same thing, but in a more clever approach. So what happens now? The blocking becomes rows and columns, or what some biometricians might or breeders might call. So I talk about rows and columns, but some people might talk about rows and range, and I think there's also another term. So again, something where the terminology is not very homogeneous. But again, we got this row information, we got the column information, and we can put this in as blocks. In an ANOVA model, this was not possible to calculate because it was a fixed effect. You need a lot of information, you overfit your model, this doesn't work. Without going into the details, the random effects of rows and columns avoid this issue of overfitting and don't need this large amount of information anymore that you need for a fixed effect. It's a very clever approach, and it gives you a block effect for row and it gives you a block effect for column. Additional to that, it also allows us to put things in like a spatial effect. This AR1 model is one way to calculate spatial effects. What it basically does is this model assumes that the error in plots which are really closely together is higher correlated than the error of, for example, this plot and this plot. And that makes sense. We would assume that the conditions here are very similar, that the conditions here are very similar, and therefore the errors here are highly correlated, the errors here are highly correlated, but the errors here and here are not highly correlated. They are almost independent. And well, it turns out that putting these three factors in general, is a really, really, really good way to correct for that. Now we can optimize this. And well, if you have the time, if you're in academia and you want to publish a paper, you can spend 3 months to find the best model that works best to get the best output and the lowest error for this experiment. In practice, this is not the case. We don't have that time. So even, well, the industry, the big players don't talk much about it, but we know from some of them that they have pipelines. KWS, Pioneer, or now Corteva, they have pipelines that they use every year with the same model, because this model is very robust and it allows, if we put all our data through the same model, which does a really good job, we get really good data or really well-corrected data, accurate data, within a very short time. So, well, this is the theory. In practice, this would mean that hopefully at some point with the CG, with the programs, we get to a point where we have a relatively unified way to collect data and a relatively unified approach to breeding trials, and that would mean for the biometricians that they can have a pipeline and analyze data of many breeding programs in a very, very short time, because they don't have to spend days on cleaning the data, they don't have to spend days on unifying the data, they don't have to analyze an RCBD and an alpha lattice and row column design, but they know this is unified and we can quickly push it through. Again, this won't be the most accurate way, but practically it's probably the most reasonable, most useful way to do that. And yeah, well, again, mixed models are the weapon of choice. If you're not using it at the moment, reach out to us, because we need to find a way for you to use them, as they make a really, really big difference with regard to the analysis. This is within field trial designs. Are there any questions? And again, there's a lot of stuff, and we're not able to cover everything. It's hopefully a basic idea of things that you can easily change, more or less, without going too much into the details. Roberto, please.
Just one comment. Some years ago, I analyzed one data set from like a calf breeding program, and the breeder allocated the families just without any randomization, like the whole family in just one plot. And when you analyze the data and consider the spatial variation, so we figure out that there's another problem, because when you apply like spatial variation analysis, they try to correct and understand. So if the individuals have some similarities in terms of performance, they try to smooth this and consider, oh, the errors are forcing them to perform similarly. But if you allocate all the family in just one place, the spatial variation, you vanish the genetic signal as well. So that's another big problem, and reinforce what Chris said. So it's vital to split the family and allocate it different locations. Otherwise, the spatial variation will vanish not only the errors, but also the genetic signal, because they will consider, oh, this phenotype is quite similar. No, it's not only error. There's some genetic signal there. So that's just one empirical result that we obtained some years ago, and yeah, to be aware about that.
Thank you for that. I really appreciate when we have people from practice here that confirm what we tell in theory, because I understand sometimes the simulation results might be a bit, yeah, well, it's not real data. So I understand that sometimes it's hard to put your complete trust in these, but I can tell you that we have discussions with people working in practice, again, also sometimes with industry people, and they basically confirm what we're showing here. Unfortunately, we don't have enough data to show you things data-based, but it more or less holds through with what we get confirmed from practitioners like Roberto. Now, let me quickly check. We still have a bit to go. Yes, so I will do these couple of slides and maybe go 10 minutes over, and then sparse testing is following on Friday. We talked about checks this afternoon with Eduardo. And he already mentioned there are different types of checks. He said 2 types. I like to say there's 3 types of checks. And this is important because another term, we talk about checks, but people have different ideas of what kind of checks we talk about. Terminology, you see, is very important, and the terminology in our area is absolute crap. It's useless to communicate. We need to change that. We're trying that in the CG, but it's still, well, it's difficult. So I just want to point out, when we talk about check, there are actually 3 different types of checks. One type of checks are your benchmark genotypes, your reference for breeding, the individual that you need to put in the field to make decisions for your selection. That might be established variety, that might be, well, material from the competitor, that might be your old material, whatever. And we can't really give you any suggestions for that, because this is not a QG question. That is a pure question how you do your selections, how many checks and which checks you need in the field to make your selection. What we can give you suggestions for, however, are the steady checks and the checks for statistical analysis. So the steady checks, the connectivity checks, are basically they are what Eduardo talked about. And they play a role for measuring genetic gain for this big request from the donors. We need them to have the connection between different years to generate or to calculate our blues, which are then used to observe the increase in performance over the different years. And this is covered in a manual that Eduardo wrote. What I want to go back to are the statistical checks, the checks necessary for statistical analysis. And these are basically these checks. Back then, they were necessary. We needed many checks replicated in each of the subblocks to analyze our data. This is not necessarily the case anymore because, as I told you, the way we calculate block effects or blocking is now different. We use random effects to calculate rows and columns, and we don't need these checks in the field anymore to estimate these effects. And this becomes even easier when we have genomic data. They become even more redundant at that point. So, well, do we still need them at all? The answer is, it depends. I told you